Today we're now going to look at another amazing feature of derivatives, and in particular the graphs. You may have even noticed this when we were doing the homework assignments and progressively working through the derivatives, or the graph of the derivatives without the equations. And maybe you've already seen this observation, but let's just look in particular at this particular graph. X squared minus 5x plus 4. All right, hopefully we remember how to graph a parabola. I didn't want to know if you don't, actually. The first thing I always notice is the y-intercept, and so I know that this thing is going to cross at 4. That's always our first step. The second part of this, of course, is to find the x-intercepts. X-intercepts require me to factor, and so I'm going to do just that, x minus 4 and x minus 1. And so I find out that this graph crosses at x equals 4 and x equals 1. I'm sure you already knew that. And so there it is. So there's my graph. I don't even need to worry so much about the turning point right now. I just wanted you to see that graph. We got a quick little sketch. All right, now, from yesterday, you should have remembered, or at least I hope you remember today, how to do its derivative. And so the derivative of this would be, and sometimes you'll see this written as y prime, just because this says y, so this would be y prime, indicating that this is the derivative of y. And so to do the derivative, just once again recap what we did yesterday. The 2 would drop down in front, so 2x minus, and then the derivative of this next term, that 1 would drop down in front, making that minus 5. The x, of course, goes down to 0, or rather equal to 1. And the 4, the derivative of 4 is 0. And so the derivative equation would be 2x minus 5. So now what I'd like you to do is to graph that. And let's just see what that looks like. So the first thing I always, again, look at is that's crossing at negative 5. And then I have the slope of 2, or rather that the x-intercept would then be when y equals 0. And so just to solve that, that would mean it's at 5 halves, or 2.5, right? And so let's just see here. And so there's my graph. Isn't that interesting? What do you notice? That the graph of the derivative of a parabola happens to be a line. Interesting. And certainly there's some other perspectives. Remember how when we were earlier learning about how to graph a derivative before even having the equation, one of the things we noted was, okay, what's the derivative at that spot? That spot would have been a minimum, and so it has a derivative of 0, and you'll notice that that will line up right with that. And what do you notice here? This was decreasing, and so that part of that line would have been below, and then from here to the right, it's increasing. See how those things all link together and how it makes a little bit more sense maybe even seeing the equation. I hope that helps as we clarify derivatives even further. Now, as we're talking about derivatives, let's look a little bit more at some questions here. If we had f of x equals x cubed minus 2x, and we had to find the derivative, what would we do there? Right, we would take 3x squared minus 2. That's how we would get that. That 3 drops down in front, gives me that 3. And then we subtract 1 from its exponent, give me 3x squared. In the same way, we would drop the 1 down in front, making that negative 2, and then it would go down by 1. It would be x to the 0, which is 1. All right, well then what would f prime of c be? Well, isn't that funny? All that means is basically f prime of x in the place of that x would be c. So wouldn't that just be obviously 3c squared minus 2? I hope so. So then what would f prime of 2 be? What do you expect to be able to do there? See, another facet of these derivatives is we can now use that equation to find the slope at any point. See, what this is really saying is it wants the slope of the tangent line at 2, at x equals 2. And so all I would need once I have that equation is seriously just put 2 in for x, or c in the case above. So that would give me 12 minus 2, which is 10. Or certainly you could have done the old method of the limits. I'm sure many of you are shaking your head saying, no, thank you. All right, so let's look at this question. It says the slope of y equals x cubed minus 2x, same equation as above, at 1, negative 1. We asked you these questions last chapter. If you recall on your test, you had a couple questions just like this, and you were forced at that point to do the limit as x approaches 1 or the limit as h approaches 0 of f of 1 plus h and blah, 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 blah. You had to do that. But now we know the shortcut. And the beauty of this shortcut is rests right here, because all I need to do is find what y prime is, or the derivative of y, which we already determined in part A of these questions here, and then plug 1 in for that spot. And so it's as simple as 3 minus 2, which is 1. And that is the slope at 1, negative 1. Isn't that amazing? And that is just another facet of derivatives. See, derivatives tells us so much. And these little shortcuts, these little tricks that we have, make it so much nicer in solving that I'm sure right now you're wishing you had known this last chapter. Well, good luck as you do your homework assignment, because you'll have lots of practice with that as well on this particular packet question. In this section, you are in your homework assignment 24 through 28 that you have in front of you, hopefully. When you look through that, you'll notice 24 is just a practice through those. 25, it looks just like the question I just did there on D, where you're doing the slope at a point. Then you have your graphing practice that you have. 27 in particular, I'm just going to emphasize that some of those are just nicer if you do them using a graph. In particular, if you look at 27A and even C and D, both of those even, D, hopefully you remember what that graph is, because the truth is no matter how much calculus we do, the easiest way to do that question is going to be through using the graph. And I hope looking at that you can remember that that is a semicircle, and even more so from -2 to 0, it is the top part, but it's the top left-hand corner of that. And so it's a quarter of that circle, believe it or not. It's not even the whole thing, because it's only going from -2 to 0. So hopefully that helps you and gives you some direction. And 28, I just want to remind you of what 28 is doing. 28 is kind of looking at the graph and just asking you to compare. You're looking at the slopes and which is larger, and so if, or slopes, or rather values. If I said f of -1, what's the value of that? You can just read the graph, and f of 1, hopefully you can look at the value of that. Which one is larger? Which one, if I was talking money, would you want? And if we're looking at slope, is one positive and the other one negative? Is one 0? And in the comparison, that's what you're looking for. And actually, as I'm looking at 28, I just look right above that and see f. Isn't that amazing? You're seeing this kind of format. Now, that should not look that foreign to you, because the truth is that is Riemann sums setup for integrals. That is the whole reason for the last chapter. And hopefully when you look at that, it does not intimidate you, but you notice that equation, that summation that you have there, and you have the -1 plus, where would the -1 come from? And that 3 over n and what that means. And I'm not even going to tell you anything more than that, but I want you to think back to last chapter and all you did with Riemann sums, and even the beginning of this one, and how that looks and how that places within an integral using the S format. Good luck on your homework assignment tonight, and tomorrow we'll be talking more about derivatives and more specifically some of the special type equations that you might see. Good luck.